This session of a coordination sphere is about the theories that explains the nature and properties of coordination compounds. Let me move with the first theory, Werner's theory of coordination compounds. Let me write the heading, Werner's theory of coordination compounds. He is the first scientist who studied about the nature of coordination compounds, and according to him, the central metal atom in coordination compound. As we know, if you consider coordination compound, we have two entities. One is coordination sphere and one more is counter ion. Coordination sphere contains central metal atom which is surrounded by definite number of ligands. The same central metal atom contains two different types of valencies. Central metal ion possesses two different types of valencies, and he named it as primary valency and secondary valency. Let me write that. The first valency is primary valency, and the second one valency he named it as secondary valency. So primary valency and secondary valency are the two types of valency possessed by central metal atom. In general, if you consider any chemical compound, it has normal valencies only, but not a special kind of valencies like primary valency and secondary valency. Only in coordination compounds, the central metal atom is going to exhibit primary valency and secondary valency. The properties of primary valency is different and the properties of secondary valency is different. That is going to define the nature of the whole coordination complex. The first very important property, let me write that, primary valencies, they are ionizable, whereas the secondary valencies are non-ionizable. So very important point to identify which one is secondary valency and which one is primary valency in the coordination compounds. Remember that primary valency is ionizable, whereas secondary valency is non-ionizable. Ionization is the process actually, and this has to be used when a compound is dissolved in water, and when you get ions, that we call it as ionization. And primary valency is ionizable, means when you dissolve a coordination compound, and what actually the primary valency of central metal ion is, that undergoes ionization, whereas the secondary valency won't undergoes ionization, that we call it as non-ionizable. Primary valencies, they are balanced by negative ions or anions, whereas the secondary valencies are balanced by ligands. That is the one more difference how we can identify primary and secondary valency. Primary valency of central metal atom is going to be satisfied or balanced by anions, negatively charged ions. One example I consider, if you consider cationic complex and we have anions outside the sphere, that we call it as counter ions. And what is the charge of the counter ions we consider? That is going to balance the primary valency of the central metal ion. And inside the coordination sphere we have ligands. Ligands are nothing but the species, they have lone pair of electrons for the donation to the central metal atom through coordinate bond, the same ligand it is. So how many number of ligands, and that is going to balance the secondary valency of central metal ion. So remember that anions balances or satisfies the primary valency, whereas the ligands balances or satisfy the secondary valency. These primary valencies, they vary, whereas the secondary valency, they are fixed. So if you consider the set of examples of coordination compounds of the same elements or atoms, the primary valency will remain same, whereas the secondary valency is going to differ. One more property I will write, the primary valency is nothing but we can identify it by oxidation state of central metal atom. So one more factor to identify the primary valency is, if we calculate the oxidation state of a central metal atom, that is actually the primary valency of the central metal atom. But remember, this is not only the factor that decides the primary valency, whether it is ionizable or not, that you have to see that. So one more concept with respect to the secondary valency. The secondary valency are going to be coordinated, or that can be predicted by knowing the coordination number. Coordination number, the total number of coordinate bonds present in a complex, we call it as coordination number. So how many ligands we have, and these ligands are going to donate lone pair of electrons, so through a coordinate bond, and if you count the coordinate bonds, that itself will be the coordination number, and that itself is the secondary valency of a central metal atom. So try to know that one. Primary valencies are ionizable, and also that is the oxidation state of central metal atom. Secondary valencies are non-ionizable, and actually that is the coordination number what we consider. Primary valencies are non-directional in nature. Let me write here. They are non-directional in nature, whereas the secondary valencies are directional in nature. Secondary valencies are directional in nature. As I said, secondary valency is going to be related to ligands, and it is going to be related to coordination number. If you consider an example of a square planar coordination complex, we have a central metal atom in the center, and which is surrounded by ligands, and ligands occupy the four corners of the square, so that the shape of, or geometry, we call it as a square planar, and they are supposed to donate the lone pair of electrons towards central metal atom. We have a definite direction, isn't it? So therefore these secondary valencies are directional in nature, whereas the primary valencies are going to be ionizable, and they are balanced by anions. There is no question of a directional in nature, therefore the primary valencies are non-directional in nature. So all these are the postulates or assumptions of Werner's theory. I have written in the form of flow chart to understand it better. Try to remember, the central metal atom in coordination complex exhibits two types of valencies, primary valency and secondary valency. Primary valencies are non-ionizable, primary valencies are ionizable, secondary valencies are non-ionizable. Primary valencies are satisfied by anions, whereas the secondary valencies are satisfied by ligands. Primary valency vary, whereas secondary valency will remain the same. Primary valency corresponds to central metal atom oxidation state, whereas secondary valency refers to the coordination number in a complex. Primary valencies are non-directional in nature, whereas secondary valencies are directional in nature. All these are the assumptions of Werner's theory that explains the nature of a central metal atom and ligand and the counter ions of a coordination complex. Then how actually these are the properties explained by Werner? So he considered some set of coordination compounds of a cobalt with ligands as a Cl- and NH3, and some set of coordination compounds he considered, and he conducted observable experiment based on these compounds, and he arrived at these conclusions. So now we'll see the examples that explains how these postulates the Werner got to explain the nature of coordination compounds. So in general, let me tell you the reaction. So if you consider any compound with an ion as a Cl-, compound with a chloride, I can say, when this reacts with AgNO3, silver nitrate, when a compound with Cl- reacts with AgNO3, the basic reaction of chemistry, one can easily guess, Cl-, this is ionizable. So if you consider NaCl as an example, so after ionization we get Na plus and Cl-, isn't it? So Cl- is ionizable. So since Cl- is ionizable, that is going to be replaced, and we get white colored precipitate of AgCl, silver chloride precipitate we are going to get. That is the equation what we already know. So remember that a compound with the Cl-, when it reacts with the excess of AgNO3, AgCl precipitate we get. Of course, one more product is going to be obtained, but AgCl precipitate is the very important to identify the nature of the substance. Similarly, as I said, Werner considered the coordination compound of cobalt, and he analyzed the same experiment. He reacted all the coordination compounds with AgNO3 and what kind of precipitate we get, and based on that he analyzed the primary valency, secondary valency, and the nature of these central metal atom and ligands. So the first compound what he considered is, let me write that, CO Cl3, 6NH3. So this is the initial, the coordinate compound experimentally conducted by Werner. And if you just physically look over the structure, look over the molecular formula, it doesn't looks like a coordination compound because we don't have counter ions, we don't have coordination pair also. But let me explain later how we can write in that fashion. So this is a coordination compound Werner took, and he reacted with excess amount of AgNO3, excess amount of silver nitrate. And now if you observe the coordination compound, we have Cl3, Cl minus anions we have. So all these are ionizable, and experimentally he got AgCl as the precipitate. So AgCl precipitate he got, and he weighed the amount of precipitate what he got, and experimentally he got 3 moles of AgCl. If you consider this particular compound and react with excess of AgNO3, and you will be getting 3 moles of AgCl. Since I got 3 moles of AgCl, I can write here 3 moles of AgNO3 because that is going to react with the initial coordinate compound. So what I am going to say by this reaction is 1 mole of coordination compound treated with 3 moles of AgNO3, and we get 3 moles of AgCl. That is the initial reaction what actually the Werner took. So now based on this reaction, let me explain what is the primary valency and what is the secondary valency, and how we can write the primary valency and secondary valency of a central metal atom. So now here, since we have cobalt transition element, that actually is the central metal atom. So this central metal atom contains 2 types of valency, primary valency and secondary valency. That is according to Werner. So now, as I said in general case, the Cl minus what I consider, that should be in ion, in the form of ion, that should undergo ionization. The compound of Cl minus that should undergo ionization. Only ionizable Cl minus reacts with AgNO3, you will get AgCl. Here we have Cl3. 3 Cl we have. Since we got 3 AgCl, I can say 3 moles of Cl minus ions we have. 3 Cl minus ion. So all the 3 Cl are ionizable, and all the 3 Cl is going to be converted into precipitate. So since Cl3 we have, all undergoes ionization. So now look over the postulate what I said, primary valencies are ionizable. So these Cl3 will undergo ionization and you will be getting precipitate. Therefore the primary valency of cobalt is 3, since primary valencies are ionizable. And what about the secondary valency? The one ligand is Cl minus, one more ligand is NH3 amine. Secondary valencies are non-ionizable. So in this coordination compound, NH3 does not undergo ionization because we have AgNO3. AgNO3 is going to react with the ionizable Cl minus only to get AgCl precipitate. So how many NH3 we have? We have 6 NH3. Therefore the secondary valency I am going to write here 6. So that is how you need to predict the primary valency and the secondary valency. The very important point is primary valencies are ionizable and secondary valencies are non-ionizable. So 3 moles of AgCl is experimental data. You cannot guess how many moles of the product we get. But according to the Werner, when he took this compound and when he reacted with excess of AgNO3, he got 3 moles of AgCl. Based on that, he said primary valency of cobalt is 3 and secondary valency of cobalt is 6. One more postulate you just observe here. Primary valencies are balanced by anions and secondary valence is balanced by ligands. So to know that, we'll write the modern method of writing the compound. So this compound, how I can write in the better way. So now CO I will write, and one ligand CH3. So CO is the central metal atom, NH3 is the ligand, and how many is NH3 ligands? We have 6 NH3. So NH3 6 times I will write, and I will mention the coordination pair. And we have Cl3 which undergoes ionization, therefore I will write a Cl3. That gives the actual meaning of a coordination complex. So this is the same coordination complex, this is the same coordination complex, and if you observe this one, you didn't get the concept of which one is ionizable, which one is non-ionizable. If you write the same thing in this form, you are going to get which ion is ionizable, which is not ionizable. So how to identify which ligand undergoes ionizable? So observe here, this is the coordination pair, central metal atom. So NH3 is the ligand. Remember that the ligand what we write in the coordination sphere, always they are non-ionizable, or I can say they are the ligands, I can say, that is going to balance the secondary valency. So NH3 is non-ionizable, whereas outside the coordination sphere counter ion we have, they are ionizable. So Cl3 we have 3 Cl minus we are going to get after ionization. Therefore primary valencies are ionizable, secondary valencies are non-ionizable. So now if you observe here, Cl3 we have, and the charge, let me write 3. Okay, and the primary valency of cobalt is 3 plus. So 3 plus what we have, sorry, this is 3 minus, since Cl is anion, isn't it? Yes, sorry for that, this is actually 3 minus. So the primary valency is 3, isn't it? So 3 is going to be balanced with this 3 minus, and this Cl3 is anion. So what I am going to say, the primary valencies are balanced by anions. So in this coordination compound, Cl minus will be the anion, the primary valency of cobalt is going to be balanced with anions. Secondary valency, what is the secondary valency? Secondary valency is corresponding to the coordination number. So central metal atom CO we have, and surrounded by NH3. How many NH3? 6 we have. Octahedral complexities. How many ligands we have? 6 ligands we have. Therefore the coordination number 6 I have written. Sorry, the secondary valency 6 I have written, since the coordination number is 6. So secondary valency cobalt is going to be balanced by ligands here. So this is how I can explain why primary valencies are ionizable, why they are supposed to be satisfied by anions, and oxidation state of a central metal atom. So if you calculate the oxidation state of central metal atom in this particular compound, the central metal atom oxidation state is 3 plus, and coordination number as good as NH3 6 we have. So now we'll see why the primary valence is non-directional and directional. If you draw the structure of CO NH3 6 times, octahedral shape I mentioned. So 3 NH3 will be at 4 corners of the square planar, or square you can say, and 1 NH3 will be above and 1 NH3 will be below, so that 6 coordinate bonds we have directional in nature, whereas the primary valency, that is not at all related with the direction of that one. That is how, by considering this example, we can explain these postulates. That is the first example what actually Werner took. And then, as I said, he didn't consider only one example. He made some trial and error by considering different examples of the same kind. So this is the one example what actually Werner considered. COCl3 5NH3. The second kind of compound as a central metal atom, CO and Cl minus NH3 as the ligands. When he treated this coordination compound with silver nitrate, and now the precipitate will be getting as a silver chloride AgCl. Practically, Werner observed that when this particular compound is treated with excess of AgNO3, 2 moles of AgCl precipitate is going to be observed. Since I have 2 AgCl, I can say that 2 AgNO3 is going to be utilized. So 2 moles of AgCl is the experimental data what Werner observed. So in this particular reaction, 1 mole of this coordination compound has been treated with 2 moles of AgNO3, and we are going to get 2 moles of AgCl. So based on this reaction, we'll predict what would be the primary valency of cobalt and what would be the secondary valency of cobalt. And we need to follow the same principle what we applied for the previous example. Primary valencies are ionizable, secondary valencies are non-ionizable. Primary valencies has to be satisfied by anions, whereas secondary valencies has to be satisfied by the ligands here. Now, based on this reaction, observe here, 2 AgCl we get, means in the precipitate we have 2 Cl minus ions. So in the precipitate, since we have 2 Cl minus ions, there should be 2 ionizable chloride ions in case of the original compound. But in this coordination compounds, we have 3 Cl. See here, all the 3 Cl are not going to be ionized to get Cl as a precipitate. Out of these 3, only 2 Cl is going to be ionizable. Because of that reason, 2 AgCl precipitate we are going to get. So based on this concept, I can write the primary valency of cobalt will be 2. Whereas compare with the previous example. In the previous example, of course we have COCl3, COCl3. Here all the three are ionizable. Because of that we got 3 AgCl as a precipitate. In this particular example, not all the 3 Cl are the ionizable. Out of 3, 2 Cl are ionizable, therefore 2 AgCl precipitate we will be getting, therefore the primary valency will be 2, which is balanced by the anions. Now we'll see what about the secondary valency. Secondary valency, so in this compound, out of these 3, 2 has been utilized, we have one more. So let me write here for your reference, 1 Cl minus we have. So 1 Cl minus is non-ionizable, that has not ionizable, so that you are going to get the precipitate. We have one more kind of ligand, NH3, but how many NH3 we have? We have 5 NH3. So we have 5 NH3 neutral ligand and we have 1 Cl minus. These two are non-ionizable. Totally 1 Cl and 5 NH3 we have. Totally therefore the secondary valency of central metal atom is 6. Now, if you know the primary valency as 2, secondary valency as 6, now I can write the modern method of writing the coordination compounds. Cobalt I will write. Remember that, as I explained, in the coordination sphere, the terms what we write, they are supposed to be non-ionizable. Therefore, NH3 we have, which is won't undergo ionization. 5 NH3 we have, I will write 5. So Cl3 we have. So 2 are ionizable, 1 is non-ionizable, therefore that also I will write here and I will complete with the square bracket. So this is a coordination sphere and 2 Cl undergoes ionization, therefore I will be writing as Cl2. So try to understand, in this particular compound, this Cl, both are not identical. So Cl minus is ligand, whereas the 2 Cl minus are anions here. This Cl non-ionizable, these Cls are ionizable. Therefore, now you see how many ligands this cobalt is surrounded with. 5 plus 1 is 6. Therefore, the secondary valency we are going to get 6. Now you see, what about the anions? So how many anions we have? Cl means the charge will be 2 minus, 2 Cl minus we have. The primary valency has to be balanced with the anions. Therefore, the primary valency we have to. This is how we can verify the primary and the secondary valency what we have written. One more example he considered, that is of the same kind, COCl3. This time he is going to consider 4 NH3, 4 amounts of NH3, and he treated with the silver nitrate, excess of AgNO3, and Werner got the precipitate, that is the same thing, silver chloride AgCl we got. But when this coordination compound treated with the AgNO3, practically experimentally he got 1 mole of AgCl, 1 mole of AgCl precipitate he got. Since 1 mole of AgCl means 1 mole of AgNO3 is going to be used. So this equation I can say that 1 mole of this coordination compound treated with 1 mole of AgNO3 and 1 mole of AgCl precipitate we got. So try to understand, in this particular case 1 mole of AgCl we have, means 1 Cl minus we have. But in the original compound, how many Cl we have? 3 Cls we have. So not all the 3 Cls are converted into precipitate. Out of 3, only 1 is going to be converted into precipitate after ionization. Therefore, the primary valency of cobalt in this compound will be 1. Then what about the secondary valency? Secondary valencies are non-ionizable. Secondary valency, out of 3, 1 undergoes ionization and converted into precipitate. We have 2 more. Therefore, 2 Cl we have. Minus you can write. So we have one more ligand NH3, but how many we have? We have 4 NH3, totally 2 plus 4 we have 6. Therefore secondary ligand, secondary valency for this particular cobalt is 6. So remember that primary valency is 1, secondary valency is 6 for this particular compound. And now modern method of writing the coordination complex. So central metal atom CO, as I said, coordination sphere, the terms should be non-ionizable. So NH3 I will write. How many NH3 we have? 4 I will write here. And one more ligand we have, that is Cl. But how many Cl we have? We have Cl2, 2 Cl. And outside the bracket, that should be the ionizable, and only 1 Cl undergoes ionization. Therefore, I have written only 1 Cl. So this is how the modern method of coordination compounds can be written. So these are the 3 examples what actually Werner took to explain the postulates of coordination compounds. Now if you just observe, in short I will tell you, all these 3 coordination compounds are of the same kind of central metal atom, cobalt only. We have 2 different types of ligands, one is chlorido and one more more is amine, Cl minus and NH3, but the amount of will be different. Here 6 NH3, here 5 NH3 and here 4 NH3. That is not going to be considered, but how many moles of precipitate we get when it is going to be treated with AgNO3 is a very important point. Remember that I have not written randomly this 3 AgCl, 2 AgCl and 1 AgCl. These are the experimental data observed by the Werners. So in this compound 3 AgCl we get, so therefore the primary valency will be 3. In this compound 2 AgCl we get, therefore the primary valency will be 2. In this compound 1 AgCl we get, therefore the primary valency will be 1. So what I am going to say, primary valencies are ionizable, whereas secondary valencies are ionizable satisfied by the ligands. Therefore the remaining what we have, secondary, what that we are going to write. So one more very important point I am going to highlight here. So same kind of compounds we have, primary valency 3, primary valency 2, primary valency 1, primary valency vary, secondary valency 6, secondary valency 6, secondary valency 6, secondary valency are fixed. I have written the point here where it is, yes, here we have primary valencies are going to vary, secondary valencies are fixed in a coordination compounds. They are directional, secondary, whereas primary valencies are non-directional. So all these are the postulates given by Werner to know the concepts of coordination compounds and the nature of ligands as well as the central metal atom. Now I consider one particular problem from NCERT textbook. They have given some list of formula and they have mentioned the number of moles of AgCl precipitated when these coordination compound has been treated with AgNO3, and you need to calculate the secondary valencies of central metal atom. So the same principle has to be applied, just I explained by considering cobalt coordination compound. So in the first column we have the formula of coordination compounds. How many moles of precipitate we get? AgCl will be the precipitate, definitely, and we need to write the secondary valency of that. And one very simple method you just remember, number of moles of precipitate they will mention, because that is the experimental data. So how many moles of Cl minus we have, and that amount of Cl are ionizable and remaining are non-ionizable. That corresponds to the coordination number and the secondary valency. So now see the first example, PdCl2 4NH3. When you treat this particular coordination compound with AgNO3, we get 2 moles of AgCl. Since we get 2 moles of AgCl, means in the original compound we have 2 Cl which are ionizable. So in the compound we have 2 Cl which are ionizable, means the primary valency will be 2, but they have asked what about the secondary valency. So since both Cl are ionizable and we are not left with any Cl which are non-ionizable, we have NH3, 4 times of NH3, therefore the secondary valency of cobalt in this particular, secondary valency of PD in this compound is 4. In the second example, NiCl2 6H2O. When you treat this compound with AgNO3, 2 moles of AgCl we get. Since 2 moles of AgCl as a precipitate, in the original compound 2 Cl should be ionizable. In the initial compound we have Cl2, all the Cl undergoes ionization, has been converted into precipitate, therefore we are not left with any Cl, we have H2O 6 times, therefore the secondary valency will be 6. I am going to write the only secondary valencies. Primary valency you can calculate how many precipitate and how many ions are going to be ionizable. Third example, PtCl4 2HCl. If you treat this compound with AgNO3, and here we are going to get 0 moles of AgCl, we are not going to get precipitate also. Then since we are not going to get any precipitate, so all the Cl, all the 4 Cls are non-ionizable, they never undergo ionization. So we have a 4 Cl which are non-ionizable, that contributes to the secondary valency, and we have 2 HCl also, totally 4, and here we have 2, therefore secondary valency will be 6. COCl3 4NH3. When this compound is treated with AgNO3, 1 mole of AgCl, 1 Cl minus precipitate, means in the original compound definitely 1 Cl should be undergoes ionization, but here we have 3. So out of 3, 1 undergoes ionization, 2 are non-ionizable. So 2 are non-ionizable and we have 4 NH3, totally 2 plus 4, 6 is the secondary valency of cobalt. In case of platinum compound, PtCl to 2NH3, we are not going to get any precipitate. Means all the Cl are non-ionizable. Means you need to consider these 2 Cl2 and 2 NH3 we have. Therefore, the coordination number will be, the secondary valency will be 4. Remember that the precipitate, if you get, and number of moles of the precipitate, that will be as same as the Cl minus present in the original compound of coordination compound. This is how one can identify the secondary valency. Similarly, primary valency will be very easy. That is going to be balanced by the anion. We can calculate that. That is how, using Werner's theory, we are supposed to calculate the primary valency and the secondary valency of coordination compounds. Now, I consider such examples. We'll try to see what is the difference of these compounds. So one particular example I am going to consider, and that particular compound is potash alum. Name I have written, potash alum. And the formula of potash alum, let me write here. Potash alum formula is K2SO4 Al2SO4 thrice 24H2O. This is the formula of potash alum. One more example I consider, Morse salt. Morse salt. And we have some other names for this. You can call it as FAS also. FAS stands for ferrous ammonium sulfate. Remember, FAS stands for ferrous ammonium sulfate. You can call it as Morse salt also. So let me write the formula of this FAS, ferrous ammonium sulfate. FeSO4 NH4 twice SO4 ferrous ammonium sulfate, and we have a 6H2O in this particular FAS. So two examples I considered, one is potash alum and one more is FAS, ferrous ammonium sulfate or Morse salt. K2SO4 Al2SO4 thrice 24H2O potash alum, and that is the same potash alum what we studied in the chapter called surface chemistry. Potash alum acts as a coagulating agent that coagulates the impurities present in water so that purification of water can be done. The formula is this one. Morse salt FAS, FeSO4, NH4 twice SO4, 6H2O. In the first compound we have 24H2O, here we have 6H2O. That means these compounds are hydrated compounds, and this we call it as water of crystallization. Both are crystals only. So 24 amount of water we have and 6 amounts of water we have, water of crystallization we call it as. So now this is a kind of a compound what I have written. And since we studied many examples for coordination compounds, cationic complex, anionic complex, and these examples what we studied, and these two examples looks alike, but these are completely different. So these kind of examples we call it as a double salts, and till now what we studied about the coordination compounds, we know the name complex salt. So now we'll see the differences between these two, double salt and complex salt. So let me write here, double salt, and one more that we studied already, that is the complex salt. Both are completely different here. So these are the examples for double salt. So let me explain the nature and properties of that one. In double salts, actually we have two simple salts, whereas in case of complex salt we have complex ion, the salt containing a complex ion. So double salt contains two simple salts. How it is that? Just observe here, K2SO4 is one salt, Al2SO4 is one salt. So two simple salt will combine with respect to definite amount of water. A double salt is going to be formed. Therefore the salt containing two simple salts is called double salts. The salts containing complex ion, complex ion is nothing but the charged species containing central metal atom surrounded by the ligands, we know. Therefore here we have a two simple salts and here we have a complex ion. In a double salt we don't have coordinate bond, no coordinate bond. We are not going to observe any coordinate bond, whereas in this case of course we have a coordinate or dative bond. Coordinate bonds is formed when a ligand is going to donate the lone pair of electron to the central metal atom. There is no question of ligands and the central metal atom, so there is no presence of coordinate bond in case of double salt. Of course we have a coordinate bond in case of a complex ion. So if you consider double salt and if you consider complex salt, double salt is going to possess normal valency, whereas the complex salt, as we know according to Werner's theory, it is going to exhibit primary and secondary valencies. We have two types of valencies, primary and secondary valency. So normal salt, the double salt, it contains normal valencies, okay, +1 +2 like that, whereas complex salt has primary valency and secondary valency according to Werner. And in this case, in case of double salt, it loses identity. It is going to lose identity when dissolved in water, or I can say in aqueous solution. So when you take double salt, when you dissolve in water, that loses its identity, whereas the complex ion retains its identity. So these are all the differences between the double salt and the complex salt. So try to know that one. These two are the best examples I can give, potash alum and more salt or FAS. So these are formed by two simple salts and it has the normal valency. Of course the coordination bond will not be there, and here these are going to lose identity when dissolved in water. So when you dissolve in water, the property of potash alum is going to lose, and individual properties of K2SO4 and individual properties of Al2SO4 thrice is going to be get. Whereas in case of a complex ion, even though if you dissolve in water, even though it undergoes ionization, it does not going to lose its property will be same in case of aqueous solution or water. That is the main difference between double salt and complex salt. Then what is the comparison between in these two is, remember that in a complex salt also, in a double salt also, these are all addition compounds. We don't have a single kind of cation, we don't have a single kind of anion, we have addition of species. So these two in general we call it as addition compounds. So addition compounds can be classified into two types, one is a double salt and one is a complex salt. So any compound which has a complex salt, that we call it as coordination compound, and that is completely different with the simple concept of a double salt. That is the differences between double salt and complex salt. Coordination compounds exhibits the property of isomerisms. Yes, not only organic compounds but also inorganic compounds, especially coordination compounds, exhibits the property of isomerism. We'll see now how actually the isomerism property is going to be exhibited. So the heading, let me write isomerism. Complexes, or I can say two or more complexes which contains same molecular formula but differ in the arrangement of atoms, we call it as isomers, and the phenomenon is called isomerisms. In short, I can say complexes having same molecular formula but differ in arrangement of atoms are called isomers, and the phenomenon is called isomerism. We have two different types of isomerisms in coordination compounds. The first one is structural isomerism. And the second one is stereoisomerism. So one is structural and second one is stereoisomerism. As the name indicates, in case of structural isomerism, of course we have complexes of same molecular formula, but the structure or bond type involved in the complex is going to vary. In case of stereoisomerism, of course it has the same molecular formula, but the arrangement of ligands, arrangement of atoms in the space is going to be differ. So based on the arrangement, we have two different types of isomerism, structural isomerism and one more is stereoisomerism. So now I am going to highlight about only the first one, that is structural isomerism. So the complexes having the same molecular formula but differ in structure, or which are going to differ in bond type, are called structural isomers, and the phenomenon is called structural isomerism. Only the keyword I have written, but while defining you have to define in a proper sense. Structural isomer is different, structural isomerism is different. Complexes having the same molecular formula but differ in structure or bond type are called structure isomers, and the phenomenon is called structural isomerism. In structural isomerism, we have subtypes. Let me explain that. The first one is ionization isomerism, and the second one is linkage isomerism, and the third one is solvate or hydrate isomerism, and the fourth one is coordination isomerism. So we have 4 subtypes in the heading structural isomerisms. In all these 4 types, ionization, linkage, solvate and coordination, of course the molecular formula will be same, but the structure is going to be different, or I can say the bond type is going to be different. So in what way actually the bond type is going to be different, that depends on individual type of structural isomerisms. Let me move with the first one, that is ionization isomerism. So let me write that one. The first one I am going to talk now. The first one is ionization isomerism. So now let me consider an example of ionization isomerism. So I consider CONH3 5 times Br. This is one coordination compound, and one more I will consider, that is CONH3 5 times and SO4 and Br minus. So here I have not written the counter ion. Actually you should write that counter ion. Let me write here. So the counter ion is SO4, and this is one coordination compound. So counter ion we have, it will be Br minus. Okay. So now if you observe carefully this coordination compound, so we have in both the cases we have a cobalt as a central metal atom, and NH3 and Br will be the ligands, and SO4 will be the anion, and here these two are the ligands, and here we have the counter ion. The molecular formula will be same, the amount of these different species will be same, but what is the change if you observe here is, so now as I said, ionization isomerism. Ionization is the word to be used when you dissolve the particular compound in water, so that ions we are going to get. So now observe here, when you consider this particular compound and when you dissolve in water, we'll write what kind of ions we are going to get. So let me write here, we are going to get CONH3 5 times Br we get, okay, and we will get one more compound SO4. The charge of this will be 2 minus and the charge of this will be 2 plus. When this particular compound undergoes ionization, or when you dissolve in water, we get CONH3 5 times, we get SO4, and that is the coordination sphere, okay, and plus we will be getting a Br minus, and the charge will be 1 minus, and here it is plus. So now observe the ions what we get in these two cases. We got this particular compound as the cation, anion is SO4 2 minus, and this will be the cation, and anion is Br minus. So anions are different, and of course the counter ion is different, and coordination sphere is also different. So after ionization we got 2 different ions here. So the complexes having the same molecular formula but differ in ions formed after ionization. After ionization means when you consider these complexes and when you dissolve in water, the ions what we get, the ions are completely different even though the molecular formula is same. So such kind of isomerism, such kind of structural isomerism, we call it as ionization isomerism. The keyword let me write here. So the compounds or complexes having same molecular formula but differ in but differ in ions formed, on ionization. So that is considered to be the first one, ionization isomerism, and the phenomenon is called ionization isomerism, you can say. So the second one I am going to move with that one, and the second one is linkage. So linkage isomerism. So the second one is linkage isomerism. So let me write an example of linkage isomerism. So the example what I am going to consider here is CONH3 5 times, NO2, and the charge of the complex is 2 plus, and one more complex will be CONH3 5 times, ONO I have, and the charge will be 2 plus. So now just observe these two coordination compounds. So these two coordination compounds, we have a cobalt center metal ion, and NH3 and NO2 we have, and there we have ONO, that is as good as NO2. So what is the change in this case is, so now observe here, NH3 is more oriented ligand and NH3 is more oriented ligand, in particular neutral ligand you can say. But if you consider NO2 and here if you consider ONO or NO2, that is the best example for ambidentate ligand, isn't it? So ambidentate ligand is nothing but the ligand which has more than one donor atoms, but when complex is formed, only one donor atom is going to be attached with the central metal atom. So in this particular example, nitrogen is going to attach with the cobalt. In this particular example, oxygen is going to be attached with the cobalt. So this ligand we call it as nitrito-N, and this ligand we call it as nitrito-O, or you can call it as a nitro-N, you can call it as a nitro-O also, or in general nitro and nitrito we can say. So since these two are ambidentate ligand, here nitrogen will be the donor atom and here oxygen will be the donor atom. So they are going to link with the central metal atom, therefore the name we have linkage isomerism. So the complexes having the same molecular formula but differ in ligating atoms of ligand. I repeat, they are supposed to differ in ligating atoms of ligand, and such kind of complexes we call it as linkage isomers, and the phenomenon is called linkage isomerism. The keyword I am going to write here, the complexes having same molecular formula but differ in ligating atoms, differ in ligating atom of ligand are called linkage isomers, and the phenomenon is called linkage isomerism. So nitrogen will be the ligating atom in this case and oxygen atom will be the ligating atom, since these are ambidentate ligands. So that is about the second kind of a structural isomerism, that is linkage isomerism. So the third one will see solvate or hydrate, solvate, or you can call it as hydrate also, solvate or hydrate isomerism. So let me consider one example to explain the solvate or hydrate isomerism. One can guess H2O will be the main thing. So one example let me write here, CrH2O 6 times with Cl3. All these are NCERT examples only. And one more example I consider CrH2O 5 times Cl, that is in the coordination sphere. We have Cl2 and we have H2O. So these are the examples what I am going to consider to explain solvate or hydrate. Solvation, hydration, solvate, hydrate, the same thing. So now if you observe these two compounds, of course the molecular formula is same. See, we have 6 times of H2O we have, and 5 H2O plus 1 6 H2O. So Cl3 we have, and 1 Cl here and 3 Cl we have. So molecular formula will be the same. Then what is going to be differed here is, now you observe how many amounts of, how many quantity of aqua or water we have in the coordination sphere. In a coordination sphere we have 6 water molecules, whereas in this compound inside the coordination sphere we have 5 water molecules. So water of hydration is going to differ. So the complexes containing same molecular formula but differ in water of hydration are called hydrate or solvate isomers, and the phenomenon is called the solvation or hydration isomerism. So here they are going to differ in water of hydration, water of hydration. So that is a keyword to be written in the definition of a solvate or hydrated isomerism. The last one in case of structural isomerism, that is coordination isomerism. Let me write that one. Coordination isomerism. So we'll see one example. What is the change we get in case of coordination isomerism? Let me write that. We have a compound of chromium as NH3 ligand, COCN 6 times, that is one coordination compound, and one more I consider CrCN 6 times, and one more will be of cobalt with NH3 6 times. And if you observe these two examples, this is one example, this is one example. If you observe these two examples, try to understand we have two coordination pair that is as good as the double complexes these are, isn't it? So these are double complexes. This is one coordination compound and this is one coordination compound. Double complexes, these are examples for. So now what makes these two compounds add as coordination isomers is, now here the central metal atom is Cr, the central metal atom is cobalt, central metal atom is Cr and central metal is atom is Co. When central metal is atom is Cr, so NH3 will be the ligand, and in this case Cn will be the ligand, but in this case with chromium the ligand is going to change, so Cn will be the ligand, and in this compound of course the central metal atom is Co, the ligand is going to be NH3. So the type of ligand has been interchanged from one coordination pair to one coordination pair. So the complexes having the same molecular formula but differ in types of ligand. So amine is the ligand, Cn is the Cn minus is the ligand, Cn minus is the ligand, and amine is the ligand. So they are going to differ in types of the ligand, and such kind of complexes we call it as coordination isomers, and the phenomenon we call it as coordination isomerism. So the key point, let me write here, they are supposed to differ in types of ligands. So that is about the subtypes of structural isomerism, that is ionization, linkage, and solvate or hydrate or coordination isomerism. Remember that in all these cases the molecular formula of complexes will be same, but only the change will be in a bond time. Because of that reason we call it as structural isomerisms. Bond type will be of 4 different types. One is ionization, linkage, and solvate and coordination. So remember that these two are considered as one example. Usually in isomerism we consider two compounds or two or more compounds and we compare that because the molecular formula will be same. So these two are considered as one example. In this particular example molecular formula is same, but they are going to differ in the ions formed after ionization. So completely different ions we get, that is corresponds to ionization isomerism. In the next example what I consider here, NO2 is ambidentate, ONO is ambidentate, nitrogen will be the ligating atom, oxygen will be the ligating atom. So these two compounds are going to differ in ligating atoms of ligand, therefore these two belongs to linkage isomerism. In case of this particular compound, in the coordination pair we have 6H2O, in the coordination pair we have 5H2O, water of hydration is going to be differed, therefore these two belongs to solvate or hydrated isomerism. In this particular example the type of ligand is going to be differed, therefore these belongs to coordination isomerism. But while defining, you should define in a systematic manner. One example I will give you. If you want to define ionization isomers and ionization isomerism, the statement how you are supposed to write is complexes having the same molecular formula but differ in ions formed after ionization are called ionization isomers, and the phenomenon is called ionization isomerism. In case of linkage isomerism, complexes having same molecular formula but differ in a ligating atom of ligand are called linkage isomers, and the phenomenon is called linkage isomerism. In case of solvate or hydrate isomerism, molecules or complexes having same molecular formula but differ in water of hydration are called hydrate isomers, and the phenomenon is called hydrate isomerism. In case of coordination isomerism, complexes having the same molecular formula but differ in types of ligand are called coordination isomers, and the phenomenon is called coordination isomerism. This is the right way of defining, and you are supposed to define in the same manner. And the one example I considered, and by considering the examples you can guess what kind of the type of structural isomerism is. If I consider any one particular example, any two comparable examples, and by seeing the examples you can guess what would be the type of the structural isomerism. In simple way I will tell you, one of the ligand is ambidentate, then definitely that kind of examples will be for the linkage isomerism. So we have identical kind, and one is outside the sphere and one is inside the sphere. This kind of interchange, if you observe, that kind of example is definitely for ionization isomerism. If we have double salts and we have different types of ligands, two ligands are going to interchange, and that is going to be definitely coordination sphere. Hydrate isomerism will be very simple, because in the coordination sphere definitely H2O will be there, but the amount of H2O will be completely different. That corresponds to hydrate isomerism. This is how, if you have example, you should know how to predict what kind of structural isomerism is. That is all about the first type of isomerism, that is structural isomerism. Stereo isomerism I am going to discuss in the next session.